Hopefully you took some time to think about letter G in the context of snow accumulation and came up with the following conclusion. If you go back to read your answers back to yourself from letter F, but try to use the capital F notation, try to phrase to yourself what this answer says. Capital F has an absolute minimum of 0. Capital F has an absolute maximum of 6.5. So remember the idea that capital F was measured in inches? And when I go back, I can remind myself that's what these areas represented, the total number of inches of snowfall. Let's think about that again in context. If capital F is a number of inches, then the number of inches is at an absolute minimum at 0 inches. And the number of inches is at an absolute maximum when it's 6.5 inches. So in terms of snow accumulation, I think that's the easiest way to phrase it. That the absolute minimum number of inches of snow is 0. And the absolute maximum number of inches of snow is 6.5. So again, if you were looking out a window at the snowfall and expected to look out and see the smallest possible amount of snow on the ground, it certainly stands to reason that 0 is the smallest amount of snow you could possibly see. That would be if there's no snow at all. So the minimum number of inches of snow, or the minimum amount of snowfall, if you want to say it that way, is 0 inches. Whoops. Likewise, if you think about the absolute maximum, the maximum number of inches of snow, or the maximum amount of snowfall, is 6.5. Which again means that if you looked out the window and happened to catch the absolute maximum, the highest amount of snowfall that you would ever see, you'd see 6.5 inches of snow. Which again makes sense, because if this table tracks the amount of snowfall, then yeah, the highest amount of snowfall, the most we've seen, is 6.5 inches. It increases and increases and increases and increases. Till then, that was what we saw about our graph, remember? It increases and increases and increases till you get to time 3. Well, sure enough, that's why. It's because time 3 is where this graph hits a max. Time 3 is when we say, we've hit peak snowfall. Words are hard. We've hit peak snowfall at time 3. We've hit 6.5 inches. Well, after that, it's going to decrease a little bit. After that, it's going to decrease all the way down to 2.5 inches. So things must have been melting for a little while. That actually kind of makes sense even in the context of the question. Remember it said at t equals 4, snow is melting at 4 inches per hour? No wonder. Snow is melting at time 4. And that's why. It's because at time 4, right about here, the amount of snow was decreasing. So of course it was melting. I was getting smaller and smaller there. Now, when I'm at time 5, I expect to see another increase. And sure enough, at time 5, look at my table. The amount of snowfall goes back up. Up to 3 inches, up to 3.25 inches. This is getting exciting, except, oh crap. Yeah, it seems we peaked again at 3.25. Because after that, the amount of snow drops again, and that makes sense because our graph was decreasing, our function was decreasing. So if we think about it, it does stand to reason that the absolute highest snowfall we saw was 6.5. It dipped a little bit down, not too far down. It went up a little bit, but not very far up, and then it went back down again. So realistically, we can tell that the answers that we got for max and min totally make sense. Even when our snow started to melt and we saw a decrease in snow, it never really melted completely, which is why the absolute min remains 0. Because even when the snow melted, it wasn't gone entirely. The minimum amount of snow was still 0, which is what we started with. But as we tracked the rise and fall of the snow levels, we definitely saw that the absolute highest it would go after that first 3 hours is definitely 6.5 inches. So hopefully that makes sense in context of snowfall, and that you can put that in your own words in question letter G if my words don't suffice. Now let's make sure that we think about this in, again, calculus terms so that we can continue to evolve our understanding. In letter H, it says, recall that we can analyze the concavity of big F by examining its second derivative. Now, concavity is going to be a whole nother layer of this that I want to make sure we understand. So, let's think about what we know about the word concavity. Concave means second derivative. Concave up, concave down, second derivative. So it says in part 1 here, since big F prime is equal to little f, what's big F double prime? So let's just go back and make sure we understand. This was something we established in the previous page. This was something we established in part C. The big F prime is the same thing as just little f. Big F prime, same thing as little f. We established that in part C already, so I'm just going to make a note to myself. This is a previous result that we already have from part C. So let's think. Big F double prime is like the derivative of big F prime. Well, I already know what big F prime is. We established that. So if big F double prime is just the derivative of big F prime, then that means that little f must also need a derivative. If I'm taking the derivative of the left side of this statement, then I'm really just taking the derivative of the right side of this statement. That seems to make sense. So big F double prime must be equal to little f single prime. Now, if you're looking at that and asking yourself, okay, so what? How is that helpful? Think for a moment. We still don't know much about big F, and we never made a table for big F double prime. We have big F regular in part B, but the only other table we had was big F prime. We don't have any information about big F double prime. So what in the world are we supposed to do to get big F double prime? What does that have to do with anything? And I'm going to look at part 2 for a second for a context clue. It says, what did big F double prime have to do with the graph? Well, that seems strange. Why would I look back at the graph? The graph is little f. Oh, wait. That's the missing link. Big F double prime doesn't have to do with the graph, but little f does. Little f prime is something I can look at the graph to interpret. Think about that for a second. What would little f prime have to do with a graph? In the context of a graph, a derivative, a prime, is a slope. So in reality, this little f prime notation is really talking about the slopes of my graph. That's the interpretation that I need to solve problems with big F double prime, where I have no freaking idea what big F looks like. I have no graph for big F. I have no information in a table for big F. I'm lost. I'm not going to use big F. If I need to analyze big F prime, that's the same thing, apparently, as analyzing the slopes, or the derivatives, of little f. So I can look at a graph and find slopes. That seems doable. These are all just straight lines. That looks completely doable to me. So let's see if we can make some sense of that in part 3. In case you're wondering, I'm skipping part 2, but only because I've articulated it in part 1, and you can put it on your own words if you want to. What does big F double prime have to do with the graph? Well, it's the slopes of little f. It's the slopes on the graph that we're looking for. So let's see if we can do this. It says in part 3 to use the original graph of little f to construct a line chart for big F double prime. So let's parse this for a second, because that's a lot of f's to digest. If I make my line chart, I'm supposed to be analyzing big F double prime. But that's useless right now, because I don't know what big F double prime is. So I'm going to make a quick translation. I'm going to get this information from the slopes of little f single prime. That's what I'm trying to do, the slopes of little f single prime. Now, if I need to find slopes, that means I need to be looking at the graph and interpreting the graph as we always interpret line charts. I'm looking for zeros, I'm looking for pluses, and I'm looking for minuses. Now, just to make sure, I do want to give myself some boundaries here. The graph starts at 0. The graph ends at 8, so I want to make sure my line chart is accurate in that way. So remember, I'm looking for slopes. So usually I start my line chart with zeros. That means I'm looking back at my picture and I'm looking for 0 slopes. Let's look at the picture. Where do we see 0 slopes? Well, we see a slope from 1 to 2 that's flat. Flat slopes are 0 slopes. So from 1 to 2, everything looks completely flat. I'm going to put that on my line chart. From 1 to 2, all of those slopes look completely flat. Now, on a technicality, it looks like at 1 there's actually a sharp point. The slope's not technically flat at 1. If I zoom in really close there, I can tell it's not really completely flat at 1 itself. It's making that transition. So at 1 on my line chart, I should probably show that it's actually a sharp point, undefined slope. And same thing at 2. It got sharp again as the graph was turning the opposite way. So again, I'll put a little undefined, just for formality's sake. If you don't put that, that's not a deal breaker. I'm just pointing it out that it's technically true. So where else might I have some sharp points or some undefined or 0 slopes? Now that I'm looking for undefined, I should pay attention to those too. It looks like, right down here at 4, that's a sharp point. That would be critical on a line chart. So at 4, sharp point on my line chart. Then I'm going to go back. It looks like I have another sharp point at 5. That's critical. So sharp point. Then I'm going back at 6. It looks like I have another sharp point. At 7, it looks like I have another sharp point. So I'm going back and forth a little bit. That's getting kind of annoying. So 6 and 7, done and done. And then between 7 and 8, it looks like it's all completely flat. So 0 slopes in between. Okay, so I've analyzed my critical slopes, the 0 slopes, and the undefined slopes, so that's looking pretty good. The only thing my line chart is missing is pluses and minuses. And again, I'm looking at slopes, so pluses and minuses with slopes are positive slopes and negative slopes. So let's take a peek. Between 0 and 1, the first region of my line chart I want to analyze, I see all positive slopes. So this whole slope up here is a positive slope, thus plus sign. Between 1 and 2, I already know the graph is flat, so 0 slopes there. What about between 2 and 4? Between 2 and 4, that whole slope down is negative. So minus sign there. Now let's look between 4 and 5. Between 4 and 5, the slope appears to be positive. Between 5 and 6, the graph still has a positive slope. Between 6 and 7, the graph appears to have a negative slope. And from 7 to 8, again, the graph has no slope, or 0 slope. It's flat, hence the 0. Now, let's challenge ourselves. Can we interpret this in terms of concavity? Concavity occurs in 2 different ways. We have both concave up and concave down. So, let's think. Concave up, traditionally, is where the line chart has positives. So this graph must be concave up, or big F must be concave up, and I'll actually phrase it properly. Big F is concave up in the following intervals. From 0 to 1, because there's a plus sign there, 4 to 5, because there's a plus sign there, and 5 to 6, because there's a plus sign there. So the intervals of concave up are 0 to 1, in union with 4 to 5, in union with 5 to 6. By the same logic, big F is concave down in any section of the line chart where the negatives appear. So that means we are concave down from 2 to 4 and from 6 to 7, because those are the locations on the line chart, or the sections of the line chart, where I see the negative signs. Now, the last little bit of this question, points of inflection, have to do with where the concavity changed from positive to negative. Now, I'm looking at all these numbers thinking these are possible points of inflection, but I want to make sure that I remember not every number on the line chart is an inflection point. The only places that count as inflection points are places where the concavity switches from positive to negative or negative to positive. So for instance, time 1 doesn't count because the concavity switches from positive to 0, but that's not a full switch. Positive to 0 doesn't mean anything. So time 1, useless. Time 2, also useless. Switch from 0 to negative, nah, that doesn't do anything. But time 4 is a good one because we go from negative to positive. Time 4 is definitely an inflection point. And time 5, nope. Time 5 couldn't be because I'm positive to positive, so that didn't really switch. Time 6 is good though, because I switched from positive to negative. So time 6 is a possible inflection point. But time 7 is useless because negative to 0 doesn't do anything, and time 8 doesn't tell us much because we don't know what's happening after 8. So now I have all of my answers for concave up, concave down, and the inflection points. I'm going to make one last challenge for you to try to think about on your own. What do you think this has to do with snow accumulation? This is a tougher stretch, but what do you think this has to do with the snow? I'll pose that as an open question. In the next video, I'll answer that question, and we'll tie it all together to finish the page.